from Universidade de São Paulo, who's going to talk on the global solvability versus global hypoellipticity on compact manifolds. Thank you so much.
Thank you very much for the introduction, Mariana. And first of all, I'd like to thank the organizers, Alexandre and Luis, for the kind invitation. And I also should thank FAPESP for their financial support. And this talk is loosely based on a couple of ongoing projects of myself together with a few combinations of these three guys down here. And although these projects they are about very different questions, I will talk about a common theme that keeps popping up over and over in this business of global solvability and global hypoellipticity. My intention with this talk is to be a little less technical than the previous ones. So in order to motivate the questions that we approach here, I would like to recall a proverbial result, which I think is due to Travis, which says in general lines that hypoelliptic operators have solvable transposes. Okay. And my question here is, what about solvability of P itself? Okay. And while in Travis' result, the actual statement is usually stated locally, in that setup, the answer of that question is in general not much, one can say. For instance, in the 70s, Kanai showed hypoelliptic operators that are not locally solvable. But here, we are interested only in global phenomena. And for that, we must recall a few basic definitions, okay? So for us here, omega will be a compact, boundaryless, smooth manifold, which for simplicity, I will assume to be orientable, and in fact oriented. And I will endow it with a Riemannian metric so that I can make a lot of useful identifications. So for instance, using that Riemannian metric, we can identify the space of Schwartz distributions globally defined on our closed manifold with the topological dual of the space of smooth functions with complex values. And this we endow with the usual Fréchet topology. And I will also consider P a smooth linear partial differential operator globally defined on omega. And we define the transpose of PV via this property, where here I'm using dV to integrate. dV is the volume form associated with our Riemannian metric that we fixed in the previous slide, and compatible with the orientation given, okay? And we see that compatibility conditions naturally arise. For a smooth function f, it lies in the range of P, then necessary, really, it's annihilated by any distribution lying in the kernel of the transpose. And this may be restated as this inclusion, meaning that the range of the operator is wholly contained in the annihilator of the kernel of the transpose. And then, if F doesn't belong to this annihilator, it's basically hopeless to expect to to solve the equation P of U equals F. And also by functional analysis, this is exactly the closure of the range. So we define, as one usually does, P to be globally solvable. Not that it is surjective, because we can't expect surjectivity in general, but we say that it's globally solvable if it has closed range, acting as a map between smooth functions. Okay. The definition of global hypoellipticity, on the other hand, is exactly what one should expect in general. But unfortunately, the way it's written here, it causes unfortunately an undesired side effect, because it forces, for instance, if a distribution U, we have that P of U equals 0, then this is certainly smooth. And then this forces U to be smooth. So this definition forces the kernel of P to be entirely contained in the set of smooth functions, which by a functional analytic argument forces such kernel to be finite dimensional. And this puts a hard restriction on the class of operators would be able to deal with. And that's something we want to avoid. So what we do is to weaken the definition of global hypoellipticity with the following tentative correction. We say here, and this notation is absolutely not standard, okay, that P is almost globally hypoelliptic if whenever a distribution U has P of U smooth, then I can't infer that U is itself smooth, but I can infer that there exists a smooth V with the same image, okay? So you can restate this and see that what we are actually doing is allowing the kernel of P to be rough, okay? The kernel of P can contain rough distributions. And actually what we are in this process, as we quotient out the kernel of P in the definition of global hypoellipticity, what we are doing is to break down global hypoellipticity into disjoint unrelated properties. That is, one that the kernel is smooth, and the other that P is smooth modulo kernel. But why exactly are we interested in such a property? Well, this is because that property, which is weaker than global hypoellipticity, it implies closedness of the range. In general, no further hypothesis needed. And I will not get into the details of the proof, but it's purely functional analytics. So it works, for instance, with pseudo-differential operators. And although it's a bit technical, it's not especially hard, which made us wonder why we didn't find it in previous literature. But anyway, in particular, global hypoellipticity implies global solvability automatically, because this property is stronger than this one, right? And we can also prove this result in other regularity categories, for instance, Gevrey, but then the functional analysis Very, very different. What about a converse? It's not actually clear at this point why I would look for a converse, but anyway, especially because the converse is obviously false in general, with very simple counterexamples. And say in the unit circle, we can take this function, which we regard as a zero order operator via, say, left multiplication. And one easily sees that it's globally solvable because this function has a single root, which is a simple zero. But it's definitely not almost GH, because while one can construct distributions in the circle that satisfy this equation, any such distribution can't be even continuous, not much less smooth. And one can look for more honest operators, like say vector fields, by using this coefficient, and the argumentation is a little bit more elaborate, but this also has this property to be GS, but not almost GH. However, there are classes of operators in which the converse is true. So in that case, we have an if and only if in this theorem, okay, in some classes of operators. For instance, for left invariant operators on a complete Lie group, the converse is always true. Just to let you know, left invariant operators on compact Lie groups, if the Lie group is a torus, then these invariant operators, they are precisely the constant coefficient operators. So my statement here is in the torus is about constant coefficient operators. And this is very rigid. Can we relax this hypothesis and still get converse in a wider class of operators? So in this work together with Igor Ferra and Luis Ragognete, we took M, a closed, connected, unoriented Riemannian manifold, and by Tm, I would know the n-dimensional torus, and we have to have a matrix, so I put the standard metric in that torus, and our universe will be this product endowed with the product metric. And in that product, we will consider this class of second order operators defined by this expression, where this is the Laplace-Beltrami operator on the first factor acting on functions. These coefficients here, they are smooth and real valued. The dx, are the usual partial derivatives on the torus. Here I am denoting by t, the variable in M, and by x, the variable in the torus. And WL are some real vector fields, which for technical reasons, I will assume to be skew symmetric with respect to the L2 metric, okay? But these are vector fields in M, just in the t variable, okay? And notice that these operators here, they are invariant by the action of the torus on the product. Here, the torus act on the whole product just by making translations only in the x variable. And in the other variable, because of this term here, the operator is elliptic in that direction. Okay, and these are two very important ingredients in this stuff. And for this class of operators, meaning that regardless of the coefficients ALJ here, and regardless of these vector fields WL, the equivalence of almost GH and global solvability hold. Actually, and this is a more or less of a side comment here, we fully characterized both of these properties for that class of operators. It is in terms of this family of vector fields with constant coefficients on the torus, which is assembled as follows. For each L, we freeze the variable t at all possible positions, and we keep generating these combinations with constant coefficient dxj's. And these are constant coefficient vector fields on the torus, not on the product. We regard them as constant coefficient vector fields on the torus. And we keep generating these vector fields and putting them in this bag. And this is just a set of vector fields on the torus. It has no algebraic structure, but its span over the real field is finite dimensional, and I can take generators for this linear span. And the property that we characterize these properties in two ways. First, that this vector value map has closed range, globally solvable if you want to. And also, which is equivalent to this one, is that the sublaplacian, that is the sum of their squares, is globally solvable in Tm. Okay, forget about the t variable. We're just working here on the torus. So these two are equivalent, and they are also equivalent to these two. Okay. And those properties that I mentioned here, because they only involve these vector fields of constant coefficients, they be easily checked by means of Diophantine inequalities involving the coefficients of the generators L1, Lr. And because of the inherent invariance of our result, you may choose whatever set of generators you think are best suited to check Diophantine conditions. You don't have to take a particular family. You choose the easiest one to do the computations. Now a couple of remarks before we move on. And for those of you who are interested in that sort of generalization, well, I certainly am. We were able to substitute in our more abstract results Tm, the torus, by a general compact Lie group in that model. But then the results and their statements are much harder to state and much more delicate to prove, mainly due non-commutative issues with the Lie group, but it can be done. And also for that class of operators, in a previous work, we characterized global hypoellipticity in terms of global hypoellipticity of that family L of vector fields on the torus. So the lesson here is that for this kind of sum of squares, this family of vector fields, it encodes a huge deal of information about our operator. And I should recall that this this model was introduced by Barostici, Ferra, and Petronilio a few years ago in the full torus. Here they were working on torus in the first variable and the second variable. And that this sort of problem has been considered before, and variations of this problem have been considered before by a bunch of fellows. Many of you are well acquainted with. Here just a small list of researchers. But now I want to talk about, in the previous slides, we were interested in scalar operators, meaning operators that map functions to functions. And now we will consider similar questions, but for vector valued operators. Again, omegas will be a closed, connected, and oriented Riemannian manifold. But E, F, and F, they will be vector bundles over our manifold. And I'll put a Hermitian matrix on them, just again to make some useful identifications. And P now will be a differential operator that maps sections of E to sections of F. And in discussing global solvability of this kind of operator, things are pretty much the same in the sense of, well, this map should have closed range. Global hypoellipticity, however, is a bit trickier simply because it usually fails, and for rather trivial reasons, as we will see in the next slide. And this hinders many practical applications that we are interested in. In my opinion, the main reason to consider systems or vector valued operators is to be able to talk properly about differential complexes like this, meaning that we have actually 3 vector bundles and 2 operators in sequence, and that their composition is 0. And well, I'm definitely interested in this kind of situation because it arises very frequently in applications in geometry, in geometric situations, like for instance, the Ram complex in differential geometry, the Dolbeault complex in complex geometry, and more generally in CR geometry. We have an analogous of these operators, but I won't get into details here. Then when we have this kind of situation, look at this second one, okay? Then it's very hard that Q is globally hypoelliptic, okay? That's because we can always, pretty much always, construct rough p-exact sections. look, if there exists a distribution in E such that P of U is not smooth, then we take F as P of U. It's a distribution value in F, which is not smooth. Then Q of F is Q of PU. This composition is 0, and this is 0, and this is smooth, obviously. But F isn't smooth. So just because there are P exact non-smooth sections of F, Q can't be globally hypoelliptic. Okay. And from another angle, look, if Q were globally hypoelliptic, then this would be a finite dimensional space. But because Q composed with P is 0, then this kernel must contain all the range of P, and it's just a too big space to be finite dimensional, usually. So there's very little hope that this to work. But again, notice that this line of argumentation kind of hints that the issue lies again in the kernel of Q. So once more we try to compensate these. We do the same approach. We release the kernel of the operators involved of any responsibility regarding regularity. Okay, so back to the one operator vector value. We say that P is almost globally hypoelliptic if whatever distribution section of E is such that P of U is a smooth section of F. We can't say that U is smooth, but we can say that there exists V a smooth section such that P of V equals P of U, has the same value. Again, we are quotient out the kernel of P so as to allow a rough kernel. And now back to the situation when we had two operators forming a complex. We may form the cohomology spaces of this differential complex. The kernel of Q divided by the range of P. And actually, we can do this either with smooth coefficients or with distributional coefficients. So we have at least two cohomology spaces. And it's rather trivial to check that the almost global hypoellipticity of P is actually equivalent to injectivity of the natural map that regards a smooth cohomology class as a distributional cohomology class. Okay, which is a rather interesting property. And to do this, it's very straightforward. You just have to unwind the quotients and see what exactly injectivity of this map means. It's very simple. What is surprising, however, is that this is absolutely independent of the operator Q. It's a property of P alone, because I formulated this only in terms of P. There's no Q here. So also this property is, I think it's a bit surprising that the injectivity of this map, it's independent of the map, the operator Q that you put here. And now if we go back to the proof of our first theorem, it's so general that it still works in the bundle value situation with little to no modifications whatsoever. So here's the statement that if a vector value differential operator is almost GH, then it automatically has a closed range. Okay, which is that statement that we have in the scalar case before. So again, GH vector valued operators are globally solvable automatically. And the final question that we ask here is the same as before. Can we get a partial converse in some interesting cases? And here I mean not scalar operators, these generalized scalar operators, obviously, but we are interested in this kind of situation arising when we have true vector valued operators. And oops. And so we started investigating integrable structures of tube type with arbitrary co-rank. Again, here, omega will be the product of closed, connected, blah, 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 manifold with an m-dimensional torus. And lambda q will be the bundle of q forms over this product with components only in the nth direction. Okay, meaning that a section f of this bundle over omega is locally written as a differential form. Well, they are differential forms which are locally written like this with coefficients depending on both t and x, but the components are only in the t's and they don't contain the x's. Okay, recall that x is the variable in the torus. And as an extra data to our problem, we take m complex valued closed, this is very important, one forms on m. Recall here that this lowercase m is exactly the dimension of our torus. And we define LQ as an operator that maps sections of lambda q to sections of lambda q plus 1, given by this expression, which yields a first order vector value differential operator. And it's an easy computation to see that these form a differential complex like we were dealing before. It's a very simple computation, which makes use of closedness of these one forms. And here's a far from exhaustive list of people who work with such structure, a few of whom is among our audience today, thankfully. And just to mention a few of many authors, but these are the one of some key papers that inspired us. And this is what we are just about to prove. We have still to check some very easy to believe, but we still have to check some tiny technical details. But this is our theorem so far. Whatever the degree in the differential complex, and recall here that we were dealing with two structures of arbitrary co-rank, okay? Then the operator LQ is almost GH if and only if it has a closed range on smooth sections. And this improves some previous results in the literature. A fairly recent one is due to Huni and Giuliani from a couple of years ago. And in this case, in their result, you are dealing only with core-rank 1 different tube structures and some extra hypotheses, and they dealt only in this. Their work is much more general than this. This is just I just picking one of the small results in their paper, but they deal only with core-rank 1 structures, and they deal only in degree 0 of the differential complex. And in this case, they show that L0 is globally hypoelliptic if and only if it's globally solvable. And notice that in their case, true global hypoellipticity, unlike this twisted almost version of ours, in the case Q equals 0, this is reasonable to study because in degree 0 there you will not find that situation. You are dealing with the first operator in the differential complex. You don't have any operator coming from behind and making the kernel too big. Okay, so this is all I wanted to talk about today. So thank you very much for your attention.
Thank you so much, Gabriel. Are there any questions?
I have a question, if it's okay. My question is that if you said sublaplacian, you said something about sublaplacian, but then of the torus. So this I didn't quite understand. Maybe you can explain.
I mean, I don't know if I understood exactly your question. The only place where I mentioned the sublaplacian is here.
Exactly here, yes.
Yes. What I said is that either one of these properties, they are equivalent to, I mean, you assemble this family of vector fields on the torus. They have constant coefficients, right? You take their linear span. It's again a family of constant coefficient vector fields on the torus, and you take some generators, a basis, for instance, of this linear span. And then you make this operator, which is the sum of their squares, which is a second order operator of constant coefficients on the torus. And we proved that these properties hold for P if and only if this sum of squares is globally solvable on the torus. And because this operator has constant coefficients, you can use, say, Greenfield and Wallach, and strategy like Greenfield and Wallach to check whether this operator has close range or not.
But it's because maybe my question is, maybe I'm overlooking something, but because they're constant coefficients and there are, is it not that this sublaplacian is never globally hyperelliptic, or Is it possible that it is globally solvable, or do you have you think it can be globally solvable sometimes? Because to me it looks like it's never globally solvable.
Well, it is, for instance, if this span is everything.
But there are of them. There should be. There is.
If this family spans the, like you said, for instance, Lie groups, right?
But then it is Laplacian. Then it
So,
would be Laplacian.
yeah. For instance, if this family spans the whole Lie algebra, then this is precisely depending on the convention of the signal, but it is essentially the Laplace-Beltrami associated with a convenient metric, which is globally solvable because it's elliptic.
So exactly. So if it is Laplacian, then but this is maybe the only case when it's globally solvable is when it's Laplacian. Because if it's not Laplacian but sub-Laplacian, then it is not globally solvable. But I'm not sure. So, but just it was just my question is, if you have sub-Laplacian which is not Laplacian and which would be globally solvable.
Okay, but then the conclusion, there's even an extra conclusion that this this operator will rarely be globally solvable.
Exactly.
If that Laplacian is rarely solvable, then so is this operator. I mean, we have here an equivalence, but I'm not saying here when this or that condition holds. But then you can proceed to check if either one of them holds in whatever situation you find interesting.
Because this
Right.
sub-Laplacian is globally solvable if and only if it's globally hypoelliptic. But if it is sub-Laplacian but not Laplacian, then it is never globally hypoelliptic. That's why it looks to me that it's not globally solvable. But you are the expert, so I don't. Was just my impression.
Professor Cordaro?
May I say something? May I, Gabriel?
Sure, of course.
I think that what's going on here is a question of terminology. What they call a sub-Laplacian is an operator that's a sum of squares that satisfies Hofmann condition. This is what we essentially study. In this case, there are cases where it is globally solvable. It's not an elliptic operator. But you are right. The operators, they have constant coefficients, and there are less than the top, less than n, it never satisfies the Hofmann condition because the commutators are always zero. I think that in this theory, what they mean sub-Laplacian in general are operators that satisfies Hofmann's condition. And in this case, you can have solvability, global solvability or not. But this is the only point. No, when the operators have coefficients that are not constant, if they satisfy Hofmann's condition, you can have both situations, global solvability or not global solvability. I think that this is the point. It's a question of terminology. What's a sub-Laplacian?
If it is not if it is not constant coefficients, then I agree with you. But it says here in the theorem, it says it has constant coefficients. That's why.
No, but it is, yeah. I think that the operators, but do the operators have constant coefficients here, Gabriel? Which operators are?
Which ones?
The L's here in the slides that you are showing.
These?
These operators, L1, yes, yes.
Yes, all of these are constant coefficient operators.
Then you don't have a Hofmann's condition. No, if you have R less than M, no?
Yeah, in the torus, yes.
Yes. But, and then what Professor Jansky is saying is that you don't have a solvability unless you are in the elliptic case, no? Is that so? That's your conclusion?
Yeah,
I'm sorry,
I guess
maybe
this is reasonable, yes.
Yes, no, I think that this is, I think that I'm just making a big confusion here. I will stop talking. I'm
No,
sorry.
that's not exactly what I was meaning, because it was because it says constant coefficients. That's why.
Yeah, but I think that this is, I think that even Gabriel agrees, no?
Yes.
Yeah, I'm sorry. Just,
Don't worry. Thank you for your comment.
I was just trying to help.
Are there other questions? So let's thank Gabriel one more time and the
Very much.
organizers for the conference as well. Go ahead.
I'm sorry, Mariana, I interrupt you. I'm sorry.